In this segment, we will discuss the brain differences between readers with dyslexia and readers without dyslexia. We'll also be discussing the neural pathways that are critical for word recognition. This graphic may look familiar to you. This is Seidenberg and McClellan's four-part processing model from 1989. What this processing model helps us understand is that there are different processors in the brain that assist students in being able to read words. At the foundation of the system is the phonological processor and the orthographic processor. When students see a printed word, the orthographic processor is activated through reading input or through writing output. The orthographic processor then sends information to the phonological processor, which analyzes speech sounds and produces speech. Phonics is where the orthographic and phonological processors connect and help students associate letters or letter patterns with individual sounds. The meaning processor then is activated, in which all meanings for that printed word are retrieved. And finally, the context processor helps students be able to select which meaning fits the context of the sentence that they have read. One thing to notice is that fluency is not a separate processor. Rather, fluency is the automatization of all of the processors working together. The bidirectional arrows are also important. Although all of our processors have separate jobs to be able to read words, they also must interact and depend on one another. So let's see how the four-part processing system helps students be able to read words. So if a student sees the word bat on a white sheet of paper, the orthographic processor takes in that visual information of all of the letters. Then the phonological processor responds in one of two ways. If the word is a word that can be read by sight, the phonological processor will retrieve the whole word pronunciation for that word. If the student does not know the word by sight, the student may associate each of those individual letters with the individual phonemes to be able to read that word. Then a multitude of meanings are retrieved for this word. So bat might be bat to your eyelashes, it might be the animal, the bat, or it might be a baseball bat. All of these meanings are called upon within the brain. Then we use context to determine which meaning makes the most sense in the sentence. So in this case, the player hit the ball with his bat. The meaning is confirmed that it is indeed a baseball bat. The important thing to remember with the four-part processing model is that students with dyslexia, they have issues with their phonological processing and orthographic processing. So we are primarily talking about the systems that are impacted are the orthographic and phonological. Students with dyslexia are generally strong in vocabulary and word meanings, as well as using context to determine unknown meanings of words. This visual helps us see the three major areas of the brain that assist students in being able to read words. So, like the four-part processing model, all language occurs on the left side of the brain. And when students see a word, the occipital lobe area of the brain is activated where letter and word recognition occurs. Then that information is sent to the frontal lobe area of the brain that handles phonological processing and word pronunciation. In between the parietal lobe and the temporal lobe, this area right here is where word analysis or sound symbol connection occurs, where students are connecting those letters or letter patterns to the whole words or individual speech sounds in words. Here's another visual courtesy from Dr. Mary Ann Wolf. She is known for her work in cognitive neuroscience and psycholinguistics for reading in the brain. So what her and her colleagues have done They have taken fMRI scans of brains of people as they are reading to determine which areas of the brain are activated. So what this visual demonstrates is that within milliseconds, within the first 100 milliseconds, we see the word appear and the visual area, the back area of the brain, take in the information and become activated. Then the visual feature analysis part of the brain is activated even more. And if the word is a sight word or a word that can be read without any letter sound decoding, this visual word form area, which is still in the occipital lobe but a little bit lower, is activated. Then there is planning. So attention is focused on matching that word or those letter patterns to the speech sounds or word pronunciation. So by the time we get to 300 milliseconds, we have the phonological area of the brain activated, as well as that angular gyrus where we match the letter patterns to the phonology of the word. And within the next 600 milliseconds, we see that the phonological area is still activated, but now we see activation in the meaning area or the semantic processes of the brain. And on the right side of the brain, we see more activation to be able to execute comprehension processes. This is another visual from Dr. Mary Ann Wolf. What this visual helps us to see is how young, typically developing readers, they have a lot of activity in their frontal lobe of their brain where phonological processing occurs. What we find from brain scans of children with dyslexia is that they have the phonological area is activated, but it is much more minimal than those of typically developing readers. This also helps us understand that, again, the best known predictors of students with dyslexia are phonological processing tasks and rapid naming. So asking students to segment, blend, manipulate individual speech sounds and words is an indication of how well they will be able to read text. Rapid naming, we often see assessments in our early grades that are timed, and that is because rapid naming is a very good predictor of overall reading capability. These images are from over 40 studies, a meta-analysis of over 40 studies of children and adults and the activation patterns in the brain as they read. So as we can see in this picture, and these are of typically developing capable readers, children have a lot of activity in that phonological area of their brain. They have a lot of activity in that angular gyrus where you are making sound to symbol connections, and they have some activation in that word form area or that orthographic processing area of the brain. They have much less activation on the right side of their brain that handles comprehension processes. What we see as they become adults is we still see the phonological area of the brain activated, but we see much more activation in that word form area where we are now reading words by sight, recognizing patterns within milliseconds. And we see hardly any, if any at all, activation in the angular gyrus where we are not decoding the words anymore. We recognize so many words by sight that we no longer need to activate that angular gyrus area of our brain as often. And then we see more activation on the right side of the brain, handling more of the comprehension processes. This is an image of typical readers compared to readers with dyslexia. So like I said before, readers with dyslexia are activating that phonological area of their brain in the frontal lobe. But what we see from readers with dyslexia that they have an underactivation of the angular gyrus responsible for the sound symbol correspondence. And they also have underactivation of that back part of the occipital lobe where sight word recognition and recognizing patterns in words occurs. Typically, developing readers have activation in all three areas of the brain. So let's see how the four-part processing model can help us distinguish which processing systems may be weak for a student. If a student reads the word dad as bad, which processing system may be weak for this student? If you guessed orthographic processor, you are correct. The B and the D are very similar, and the student just has not yet mapped those letters and the images in the back part of their brain to be able to distinguish between the two letters and assign the correct sound to the letters. The orthographic processor stores mental images of individual letters and words. What about mispronouncing record as record? If you guess the context processor, you are correct. This student appears to have the decoding skills necessary to pronounce the syllables within the word correctly, but they do not yet understand the context in which the word is used to be able to change their pronunciation for the correct word. What about cap as pass? Which phonological processor? I would have to say I see this often with students, especially young students and severely struggling readers. If you guess the phonological processor, you are correct. This student has some knowledge of short A and the sound that P makes, but they are unable to sequence the phonemes in the word correctly, and or they are unable to hold on to those individual sounds to be able to blend the word correctly. These students may sound out cap as k, a, but when they blend it together, they're unable to hold those sounds and put them in the correct sequence to be able to read the word. This is definitely an area of phonological processing, and I would want to dig deeper into this student's phonological skills. And finally, the student reads the lip of the bowl and says, "Bowls don't have lips." If you guess the meaning processor, you are correct. This student has some different meanings for the word lip, but lip of the bowl is not one of the meanings that they have within their meaning processor. Therefore, they are not able to comprehend or visualize what the text is saying. So I hope that this review of the four-part processing model and the discussion of the activation patterns in the brain can not only help you understand how students with dyslexia, the struggles that they might have and how we can need to adjust our instruction to address those weak areas, but also helps you understand more about what the brain is doing during reading. Thank you.